How's it going, everybody? In this video we're going to take a look at an overview of IP routing. Now we've already covered all of the IGPs and IGPs, OSPF, EIGRP, BGP. We've even covered the VPN section. So this section I purposely left until after all that was done, so we could take a look at the parts of routing that aren't dynamic. So this is going to be anything to do with static routing, how the router actually forwards packets and things like that. So this is going to be towards the back half of the series is going to be towards IP routing, services, security, things like that, and then I'm going to throw in network principles and things like that. So we'll talk about TCP, UDP, things like that are at the beginning of the blueprint, but are going to be actually at the end of the series. So I wanted to get all the meat and potatoes up front, and then all the non-core topics towards the back. So with IP routing, there's three main steps to routing a packet. First, you receive the packet in, and you have to do a layer 3 routing table lookup. You see, you take a look at where what the destination is, and do you have a way of getting the traffic to where it's got to go? So the idea behind that is actually relatively simple. So if you're at a four-way intersection, and you want to go to, say, if you're here in the U.S., you go to Walmart. Walmart's all over the place here in the States. So if you want to go to Walmart, there's a Walmart straight ahead of you and to your left. So if you go straight ahead, you're going to hit a Walmart, and there's a Walmart to your left if you make a left-hand turn. Well, if you go ahead and all of a sudden the road's closed, maybe there's an accident, the police have it blocked off, or there's been some sort of road construction, for whatever reason, you can't get in there. They would refer to that as an IP unreachable, meaning you can't get to the destination, so you have to be rerouted. So up ahead, before you would hit that roadblock, because the fact that roadblock would be identified, you would have to get the notice beforehand. So before you'd even head straight, you would get the update to tell you not to go straight ahead, and your routing layer 3 lookup would actually tell you to go left. So now you might say, well, how does it know that? Well, based off of reconvergence with with either IGP or BGP, that will tell you. Depending on the IGP you're using, if it's ribbed, you might get a poison reverse. You might get a what's the word I'm looking for? A max metric for OSPF or EIGRP, where you get the count to infinity, meaning that the route comes in as unreachable, and you have to reroute around the failure. So either way you get it, you're going to see relatively quickly that you can't get to where you want to go. So once you've made your layer 3 lookup, you determine which way you have to go. What you're going to do then is you're going to get switched between the incoming interface and the outgoing interface. Now, depending on how it's set up, you may or may not have to go through a software queue. Now, software queue is simply going to be how quality of service is operational. So in the software queue, that's where your policing, your shaping, your weighted random relay detection comes into play. Your any of the factors for quality of service that would affect anything you would do. So the most common things you're going to see are going to be policing, shaping, and RED, or weighted random relay detection. Now I'll talk about those briefly in an upcoming video once we're done with all the core topics and all of the peripheral, like security and services and things like that. But the idea here is to make sure you understand the details to each one of them. So that's going to be the main thing. As long as you can break down the topics here, you can break down all the topics into smaller subtopics, and you know all the details of each one of those, then you should be in pretty good shape for the route exam. The next part is going to be the encapsulation process. Now once you've moved it from, actually I should take a step back. Once you've hit the software queue, once you've made your way through the software queue, you're going to hit the hardware queue. And this is actually where the encapsulated traffic, so the frames, so layer 2 is frames, remember that. That's where the frames get serialized to the physical layer as bits, or light signals if you're running fiber. So you serialize your bits to the wire to the limit that the interface can do that at. They call that the serialization limit. And then you get forwarded out to the next hop. And then the routing lookup, the IP routing process continues over and over and over again for every packet that you receive in. There are some enhancements to that depending on how you're running. The first one we have that was a legacy version was the process switching. Process switching meant that the CPU had to make the routing decision for every packet coming and going on every interface. That was also known as the IP input process on the router. So if you do a show processes CPU sorted, and you do like a pipe include IP input, and you see that come in there, that's actually your process switching. So that means your general purpose CPU on the device is actually doing the routing for you. Some of your older platforms, that's all they could support was process switching. The enhancement to that was fast switching, which after the process switching packet was done, the lookup was done, the encapsulation was done, everything that was needed for the packet had been learned and saved. Then you would do what they call IP route cache or fast switching. Then you would forward the traffic out via fast switching. So that came in handy. That was pretty cool for a while. And then late 90s, early 2000s, Cisco came out with a product called, or a technique called CEP, or Cisco Express Forwarding. And what CEP does is it takes that IP route cache piece, and instead of you having to go out and ARP for everything and learn the next hop and all that other stuff, it does this as this routing table is being populated. So once the routing table is populated, the ARP process goes out and finds out what the layer 2 address is for the next hop. It finds out what the outgoing interface is. All that stuff is done dynamically at that point, and that's what the CEP process does. So it speeds up everything. And CEP is all done on hardware. So depending on your platform and how things are set up, you may or may not go a little faster than some platforms than others. And the reason for that is because the way that the CEP process is enabled, it might be a more software-based implementation, or it might be all hardware. Depends on if you're doing a modular router or if you're doing a like a standalone. If you're doing a standalone, or what I like to call a monolithic, the monolithic means that you have a couple of fixed ports. So, for instance, like a 3725 would be a monolithic, where a 7200 would be a completely modular. And the reason why I say modular is because there are no dedicated ports on the 7200. You would have to go in there. Well, actually, at least the ones I've worked on, they always had these slide-in modular ports. They were like 4-port for Ethernet, 4-port for serial, and then you would download the routing to the ASIC level, or to the line card, and then the routing would be done in hardware at that point. So that's a little outside of our scope here, but it's important to understand how the forwarding would work. And you can go in, and if you would like to know more about how Ceph works or how the routing architecture for a particular platform works, you can go to the datasheet, and usually there's an architecture write-up for it or a white paper on the platform that you can find that would help you, and that'll give you your actual throughput for different devices, what is tested at for a certain frame size and things like that. That's a way how I can benchmark a router against some other systems and other platforms from other vendors, and say, this is why a Cisco Nexus 7010 is faster than a 4500X for whatever reason. I can go in there and I can dig down to the details and see, okay, for your reasons, you need to go with the 7700 or 7000 series switch. That's going to be that much faster for you. Along those lines. Those white papers give you that capability. So as we move down along our IP routing review, we've already covered the switching process. The config, if you wanted to turn Ceph off, you would type in no IP route cache, and that would disable the Ceph process, which would turn everything to process switching. Now the funny thing about this is, if you turn Ceph off, what's going to end up happening is everything's going to be process switched, which it's actually kind of funny. When you want to debug something, so for instance you're wondering why a particular process is doing what it's doing, or you're wondering why you're not getting results, you can debug something. And the ironic part about it is you cannot debug a Ceph switched packet because it's not being process switched. You have to process switch a packet in order for it to be debugged. So just be aware of that if you're doing that. So, and then we get into metric versus distance. This is the age-old debate that I get into with, I just actually had a debate not too long ago with a couple of professors at a local college, and we debated this, and these are guys that teach computer sciences for a living, and I debated this with them, and the one guy claimed himself to be a routing expert, and so I was like, okay, see how much of a routing expert you really are. And so basically the idea is, at the end of the day, longest match wins. So the idea is if you have, if there are multiple longest matches, then if it's the same protocol, choose the best metric, or choose the lowest metric. And if you have different protocols, lower admin distance wins. And that's just going to be how it goes. That's why you have different protocols with different administrative distances. And personally, I'm a big OSPF fan, so if I can run OSPF, I do. If not, run EIGRP. Routers will always choose connected routes. There's no way to change that. And if you want, you can choose static routes. You can add an AD value, and they call this a floating static route. Basically what that means is, let's say for instance you have two exit interfaces on your router, and you want to prefer one over the other. You can create a static route, and by default it's a 1/0, meaning it's connected, and you're going to choose that one as a connected route. And then you can have another default route with a higher administrative distance, say of 10. And if the primary default route goes out, for whatever reason the link fails or what have you, you can fail over to the static floating route, and then that guy will take over for you dynamically. And then when the other one comes back up, it'll take over again because of the fact that it's got a better administrative distance. So the encapsulation process is actually relatively simple. You on every hop along a router's path, for a packet's path on a per hop basis, the layer 2 header is ripped off and thrown away, because the MAC address is the BIA, or the burned in address, is specific to that particular interface. So when you are going device by device, interface to interface, the layer 2 header is ripped off and rebuilt every interface that it hits, because the source and destination MAC addresses are always going to be different. The source and destination IP addresses can be the same. The source and destination IP never changes unless you do some sort of NAT, which we'll be talking about later on in the services section. So the idea behind that is, when you're dealing with multi-point interfaces, require a layer 3 to layer 2 resolution. And the reason for that is because of the fact that you might have multiple destinations available at that interface. You could look at this as an Ethernet interface. And the reason why I say Ethernet is because of the fact that you might have a LAN segment with a broadcast connection. So you might have a /24 sitting on the outside of the interface with 200 users attached to it. So that's why you use the ARP process to map a IP address to a MAC address, and then you go out. And now the reverse part of that is, I know my MAC address, I don't know the IP. That's called a reverse ARP. And then we have the frame relay, show frame relay maps, shows you what they've learned. They use inverse ARP to get that, and I'm not going to go too far into detail with that one. And then we have the recursing to and next hop. And this, we're going to talk about that when we get into policy routing coming up. And basically the idea behind this one is, when you're recursing to an interface, if it's multi-point, resolve a layer 2 address of next hop. So if you have multiple potential receivers, or multiple potential destinations, you need to have some way of differentiating one from the other. That's why you do that. If you're routing to a if you're not routing to a multi-point interface, if it's a point-to-point, you don't have to worry about it, because there's only one potential receiver and one potential destination. And then we have the default gateway, and we have the IP default network. The IP default gateway is only used if you're on a layer 2 switch or IP routing has been turned off, because then you can point your packets to the particular outgoing interface that you want to have it sent to. So you would say IP default gateway and whatever the IP address is of that default gateway, and then away you would go. IP default network is a legacy way of advertising a default route in per a classful network. And it cannot be directly connected, which means that router 1 would set it up and router 2 would receive it, but you cannot be directly connected to the connection, so router 1 wouldn't see it, router 2 would. And this is really old. I've never seen it used in production. If at worst you would use like an EIGRP, you would create a default route to a particular destination, and then do use the network command to advertise it. And then we have the default routing, where you would simply type in an all zeros route, which means if you don't have a longer match, send it out to this destination, which typically is going to be the internet, and then you would go out about. That's how you would get out to the internet from there. So IP route all zeros, so quad 0 for the subnet the prefix, quad 0 for the subnet mask, and then the outgoing interface, or the next hop IP address, or both. You can do both. And then you get into on-demand routing. This is more of a corner case scenario, but this is Cisco's flavor of routing besides EIGRP. ODR uses CDP to propagate information, and it's identified by a little o, or a lowercase o, and it's got an AD of 160. And there are some capabilities you can do with it. You can like change the administrative distance on things and stuff like that, but at the end of the day, it's a very, very lightweight routing capability. I wouldn't even call it a protocol, because there's really no protocol on the back end. It's just CDP, so it's relying on Cisco Discovery Protocol to propagate its information. And then, as we mentioned before, we have the floating static route, and the floating static route simply means that you're going to tack on an administrative distance to make the route less preferred. That's all that means. And then one of the things that we're going to talk about too, from a high-level overview, is going to be a backup interface. The backup interface is going to be a directly connected network that you're going to be able to flip over to based off of configuration. So, for instance, you can do Trax line protocol a primary interface, and if it's up, the backup interface is in standby, and if the line protocol is down, that's going to be layer 2. If line protocol is layer 2, line is physical, so layer 1. So if line protocol goes down, then you're automatically going to fail over to the backup interface. That's pretty much all there really is to it. I've never actually seen this used in production, but it is a possibility. There's actually a better way of doing this called BFD, or bidirectional forwarding detection. And what you can do with BFD, you can set this with static route or a routing protocol, is you configure BFD and then you map it to you configure it at the interface level, then you map it to a router or to a routing process, and you tie it so that it will track it. And basically, it's a lightweight hello sent between the two routers. And I can't show you in GNS3 because it will actually blow it up, because it starts sending a hello every like 50 milliseconds or something like that. It's very, very fast, very, very lightweight. It's a lot lighter. It's like a tenth of the size of an OSPF hello packet, and it's a lot faster. Where every 10 seconds you're waiting on a hello, and then you wait for a 40-second dead interval, or for the whole time. Where BFD, it's every 50 milliseconds you're sending a hello, and every 150 milliseconds you're receiving it can time out. So basically what you're doing is it's a different variation for OSPF fast hellos with the multiplier. And if you're not familiar with that, you can check out my CCIE prep video series, where I actually walk you through all the technologies on CCIE, and I cover it in detail there. And that's a good way to I've done this. I've never done BFD in production, but it's definitely a possibility to use. And you can tie it to a VRF, you can tie it to a physical interface, you can tie it to a static route. All kinds of capabilities are out there for it. But you got to be careful with BFD when you're talking about IPsec VPNs, because if, let's say, for instance, interface 1 and interface 2 are both running BFD, and interface 1 goes down, BFD will flip over to interface 2 right away and start forwarding traffic out that way. Well, if you have VPNs that are connected and they renegotiate on interface 2, and then interface 1 comes back right away, and you have preemption set up to where you can fail back over to interface 1, you might have a problem with being able to fail back over. So just be mindful of that. And that is pretty much the end of where I'm going to talk about in this video. I'm actually going to demonstrate a couple of these capabilities, like a floating static route, which is actually really, really simple. So I'll bring up my configuration here, and I'm going to go on router 9, or actually on router 7. And I'm going, because we have EIGRP here, what we're going to do is we're going to exit out of here, and I'm going to type in IP route to 0.0.0.0, 0.0.0.0, and I'm going to type in, I want to point it towards, what's my outgoing interface here? 67.00, so 67.0.0.1. Okay, now I'm going to do that one. I'm also going to do 137. I wonder if 6 isn't do show IP interface brief. Okay, good. And on 7, I'm going to do this one, but I'm going to go to the end here. I'm going to type in 100. Now, if I type in do show IP route, I should only have I should have a static default route in here pointing to 67. But if I do a do show run pipe section IP route, you'll see that I have 2 static routes. I'll have one to 67 and another one to the 137. But the 137 one will have an AD of 100. And now what I can do is I can type in router EIGRP 789 and type in network 0.0.0.0 0.0.0.0. Okay, and I can hit enter. And now if I go to router 8 and type in do show IP route, I should have a static route. I may not have propagated yet. That should be all I had to type in. And let's see, it was 9. Show IP route. Yeah, I'm learning it via BGP, and I shouldn't be. Because I'm, well, yeah, because it should be learning it via EIGRP. Either way, it's seeing it come in, even though it's pointing to router 7 via BGP. Interesting. But anyway, that's one way you can handle that. And then that's a floating static route plus trying to advertise a default. And then as we look along, the backup interface is pretty straightforward too. If I was to come up to config T and type in interface fast 1/0, type a backup interface, I could type it backup interface, and then I could say, fast 1/1 question mark and hit enter. And then if it went down, it would automatically fail over to this guy. So as you can see, it'll bounce it, as you can see, and that's that. I've never used it, so in production, so I would recommend not bothering with it. And especially when you got dynamic routing protocols in place, it'll break it. So that's pretty much what it boils down to. So that's pretty much it for this video. Next video I'm going to talk about enhanced object tracking and IPSLA, and then we're going to get into policy-based routing. And then pretty much after that, it's going to be, I think I'm going to hit up, what am I going to hit next? Oh yeah, IPv6. We need to cover IPv6, and then I'm going to get into the security and services and stuff like that, so you guys will be able to finish this series up. So I hope this has been informative for you. I'd like to thank you for viewing.